I welcome you all to this presentation on recent developments in power networks. This is a presentation regarding the power system protection aspects. Power system protection aspects means the aspects related to the electrical protection. What is power network? I will briefly try to trace the history of development of field of electrical engineering, through which the electrical engineering advancements have traveled, and having surpassed long journey, today we are in the phase of having many power stations integrated, and meanwhile the electricity invention and its accessibility are considered to be the biggest achievements of mankind. We all know. But can you believe that it was only 1878 when first incandescent lamp was discovered, and the first electric network, only DC line, it was installed in 1882 at Pearl Station in New York, which supplied only 30 kilowatt of power. So it is not more than 140 years or 150 years, 143, 44, when the light first came in the world in the form of the invention of electric utilities. So how the initial phase was there, that there was DC line, the problem was of loss in the line, because lengthening of supply lines, when we used to transfer, when you attempted to transfer the electricity from one place to another, the lines naturally were long. Lengthening of supply lines led to the problem. So how to provide supply without using too much energy in the transmission? Soon this transmission problem was overcome, where the power was generated at relatively lower voltage. It was transformed at much higher voltage for transmission, so that the losses are low according to the electrical engineering fundamentals. And then at the customer's end again it was lowered, so that he can make use of it. This was about DC line. The AC transformer came in 1885 in the first phase, or in the first phase of development. Thereafter, the AC lines came into existence. Then soon the two-phase, three-phase system, and when the electricity got transformed, we got the means to transfer it satisfactorily. There was a problem of faults in the power system. So first of all, the fuse was thought of. For example, we come with slippers on the road. Sometimes we may come with slippers on the road first time, one day. Similarly, somebody thought that why not a protection in the form of a wire which will melt after some time because of the magnitude of the fault current, and the line will be automatically switched off, or it will go off. So this way the fuse was developed. Then there was a need of automatic isolation of transmission line, but the problem with fuse was that it used to be replaced by another fuse. Here then protective relays were introduced, which will make the circuit off in such eventuality of fault time, and after some time it will make the connection back on. So this was the development of relays. Why Brown Boveri, why Boveri is used, and why Murphy are used. So these are used because they were the early scientists who worked on the area. Now, in the beginning I told you that regarding the protection engineering This is the concept. There is a generator, there is a transmission line going on, and this is a simple transmission line where some of the buses A, B, C, some of the buses are one after the other, and the transmission lines are joined in succession. The squares represent the protective relays which I am referring for protection of line. This will not give a clear picture because you will realize that if the fault is starting from A bus, if this line is isolated, then how the power will be fed to the other line. Okay. So there is actually in normal cases the situation is like this, where the multiple loops are there. Situation is like this, where whole area is covered, let us say Ajmer area, Jaipur area, Alwar area, and then integrated in this way. Okay. So this way. So these are again this is simple and small systems. 46 bus system, 14 bus system, this is 57 bus system. There are systems 223, 360 bus system, and transmission lines, they are all connecting among the various buses. There may be two lines between the same buses in the form of parallel lines also. So now we will appreciate this, that in a transmission line at either end there are two protective relays. For example, if we are giving the protection by relay named as directional oriented relays, there are two directional oriented relays at either end. For example, this pink block and this green block. So that in the event of a fault on a line, the line has to be isolated from either side. So the both relays have to operate. If one relay operates, the fault point continuously is fed by the fault current, and fault current will flow from other end to that fault point. So the fault has to be isolated from both sides. This is the theme in protection system. Now, in general psychology, if we want to speak fast, we want to act quick, we are bound to commit mistakes. Either we will make our action slow, or we may end up with a wrong action. Similarly with relays, how to be quick and accurate at the same time? They are accurate if they think over things, but it makes them slow. When it makes them slow, there can be two things. Relay fails to trip when it should trip. That means relay should act when there is a fault. It may not act. And it trips when it should not trip. That means it isolates a fault for which it is not required to operate, for which it is not intended to operate. So under this dilemma, for this small system and then for large subsystems, there are now so many relays. So what is normally expected, that in a line there are two relays at either end. So first of all, these relays should operate. Those are known as primary relays. And the such circuit breakers at either ends in the adjoining lines are also there. They are supposed to operate if the primary relay fails to operate. That means they should come for backup protection only. For example, we can realize here that fault M, that is for a fault near relay to which there is a pointer, red pointer. If there is a fault at that point, then the two black box at either end of the relay, those are required to operate. Those are known as primary relays. If they fail to operate, then the next, this at the extreme end, leftmost RMMI, that relay should operate in case that RMM does not operate. Similarly, that R for MN, that is required to operate from that side, and if that does not operate, the last one RNJ for M, that is required to operate. Why they are required to operate? Because their direction of fault current is towards the bus incoming. Okay. So this is the primary and backup protection. Now backup protection is supposed to come into picture only when primary relay fails to trip. That means we have to give sufficient time to the primary relay to operate. Okay. How it can be made possible? It can be made possible by giving the operation time or operating time of that backup relay slightly longer by setting of the range. Okay. But the problem is that that same relay, backup relay, which is at the moment for this fault M as a backup relay, for a fault near that relay will also come into picture as primary relay. At that time, its time of operation should be high. Okay. But here, the time of operation as backup relay should be smaller to that of the primary relay. So the problem is that same relay may act as primary relay at one location and it may act as backup relay for many other primary locations. But the setting of relay has to be same to perform all such conditions. So now this is the artistic and innovative area. This is not a science. This is the sheer experience of the protection engineers, that how to make the relays faster and how to make relays slightly delayed so that they may act as backup protection for some other faults. Now you will realize, or you may ask us, or anybody may will visualize that how it can be made possible, that the same relay will act faster and the same relay will act slightly delayed in such fashion by the same setting. It is because nearer the fault to a location, the fault current will be more to that location and fault current will reduce substantially as it will move away from the location of the fault. Okay, so when it will act as backup relay, the value of the fault current to be sensed or sensed by that relay will be smaller. And according to that mathematical equation, T is equal to alpha into T and in denominator, there is the action taken, that action is taken care of. Because the relay characteristic is, or rather the fault current relay characteristic is inversely proportional. That means fault current reduces substantially as the location is moved away from the fault point. So time of operation is also getting reduced. So that purpose is solved there. But still, we have to determine the setting of relays, and that is not possible. That is not possible manually. So in the research area, there a mathematical problem is found. It is an optimization problem, where all the constraints of the problem are taken together. And then all the operating time, primary operating time and this backup operating time are added in a mathematical equation for each such fault and added together under these constraints. For example, TMMI minus TMMM should be greater than some time interval by which the backup relay should act slightly delayed. So for this location we see that fault time near relay, the primary operating time is TMM. So in this equation, subject to constraints in the big block, first equation is TMMI minus TMM greater than or equal to CTI, where TMM means the fault M operating time and TMMI M means backup relay operating time, where I is a set of backup relay. Okay. Similarly, the constraint will be for other side. So all such constraints will be made. And now that was only for one pair of relay set. For a system of 6 bus, there will be 132 constraints. For a system of 14 bus, 20 lines, there will be 424 constraints. So you can realize that as the system size will grow, there will be more and more constraints, and it becomes a huge non-linear optimization problem, whose solution will be found in non-linear environment, and there will be it is a combinatorial problem making cumbersome constraints in opposition to each other. Further, the problem is that all the constraints are not feasible. So in the mathematical optimization problem, you have to take into consideration that some constraints are infeasible because of some characteristics. So you have to first identify those constraints who are infeasible, which are infeasible. You have to take out those constraints out of the problem, and then the mathematical optimization problem is actually considered. Now I will not go into the detail how the infeasibility of this productivity constraint is identified and it is overcome, because that will become too complex a matter. But for all of us to understand that how the protection is being provided by the rational control by finding their settings mathematically, I have included this particular presentation. Now the constraints and the objective function optimization problem, when it becomes too complex, we simplify the problem by considering only one side constraints. For example, near and far based approach. That means only considering this combination, first combination, TMI minus TMM. We do not consider the other end constraint for all such fault points. So the quantum of the problem is reduced, and this is known as near end fault problem or near end fault simplification of the problem. Here we are sacrificing some quality of protection by reducing some constraints. So it is emphasized recently that for a small system coordination solution based on far and far is acceptable, but in large integrated system one does not know which pair may be a critical pair. So for large integrated systems, the coordination solution based on near and far keeps system more defendable and secure. So for a critical system, we will have to take into consideration all the constraints corresponding to both sides. But for a normal system where no critical and no major devices are there and no critical and no major load points are there, we may consider this simplification. Another approach is to reduce the backup time. Backup time in the sense that so far what we are attempting in the mathematical optimization problem, that backup relay time should be greater than primary relay operating time. But one of the worry is that if the backup time is delayed by too much margin, let us say 1.5 second or let us say 3 second, 4 second, it will be of no use to us. It will be of use only insofar as that primary relay will operate first and backup relay will not operate first, so that our less area will be isolated. But if primary relay fails to operate in that time and backup relay operates too late, then it will be of no use, because by that time fault will be there on for that much time period and the damage to the system might have been caused. So there is this approach what we are doing, that we are trying to reduce the backup time. So T backup, that means operating time of backup relay is greater than operating time of primary relay by that minimum margin, but that minimum margin is attempted to be reduced in objective function so that it does not get delayed by that specified margin, let us say 0.2 second, 0.02 second, like 20 milliseconds. Okay. So this is not only a problem. That means the complexity of the problem is not only this, which I described so far regarding the primary and backup relay. There is one more problem. The problem is in the form of sympathy trips. Sympathy trips means the fault is, let us say, near a load point, let us say near this college. So the protective elements should operate near to this location only, and only that small part should get power off. Only that smart part light should go off. But what happens in the system, that fault occurs here and the relay trips somewhere, let us say near Sanganer. Okay. So unnecessarily the Sanganer people get disturbed. Okay. So this is known as sympathy trip, that somebody is in the distress and somebody else is there showing the sympathy. Okay. So this is known as sympathy trip. So this should not be possible. Rather, this should be avoided. But the problem is that if we add the another constraints in the problem, then already the big quantum of the problem will become more and the solution will not be found satisfactorily. And if that solution is will be found somehow, then that solution will not be of any practical significance, because the time period or the setting of the relays arrived so far, so obtained so, will give you so much high operating time that when the fault occurs, your protective system will not operate. Okay. So what we basically do finally in such cases, that we arrange the constraints in the decreasing order of fault current to load current, so that the less severe faults are segregated out of the system, and the maximum important constraint or the some very important area, for example, there is a collector house, there is secretariat, there is Vidhan Sabha, okay. So such important places are considered with all constraints. So protection engineering is an art. It is not a science, a definite science. It depends on the protection philosophy of the practicing engineers, their experience. Okay, and accordingly the constraints which are of very much importance are considered, and the probable solutions are found. And then recently, another concept known as adaptive protection, that is also being introduced. In adaptive protection, the fault currents are being monitored online according to the latest changing varied conditions. Okay. Then settings are calculated. That means the online settings are being calculated by the, let us say, this mathematical optimization procedure. And at the same time, these are being transferred also. But it is not so easy. It is easier said than done, because the time period again in getting the calculations, all the calculations, first of all the fault current calculation from all points, then deriving mathematical problem, then finding the optimization solution, and then transferring the settings. This can be made possible in future, because nowadays microprocessor based protective relays are there, and with the advent of the modern microprocessor relays, we can think of in the near future. Again, problem is not only of these primary backup constraints and the sympathy trips. The problem is more complicated. When, for example, let us talk about some area, let us say near this region. First of all the system is, whole system is, suddenly what happens that there some area get isolated. Now when some area get isolated, still the settings of the existing relays is not changed. That means that those relays, remaining relays, have to still act as per the protection philosophy. But problem is that when that particular part will be isolated, the load current and the fault current will change, because those three lines were creating an additional resistance reactance there in the line, and the calculation of settings was there based on the whole system in operation. Now three lines have gone out. Okay, so the protection quality is degraded. This is known as contingency, single line or contingency. For example, in a system there are 41 lines. For example, 4 lines gone. Okay, so first of all the solution has to be found with all lines in consideration. Now suddenly 4 lines gone. Now your protection setting should satisfy the present fault also, if it occurs in the remaining section. But normally it is found that this setting is not fitting to the new structure because of the fault. So what we try to consider, that we find a solution, let us say with 41 lines, then we deliberately take out one line remaining are there 40 lines. We find another solution with those 40 lines. Then we join that first line and take out another line, making it still 40, but the line is different, which is now disconnected. Sequentially we do this, and then we try to find a solution. We observe that it is not possible to consider all the single line out contingencies. In the research work, it was observed that it was possible to add only 9 single line out contingencies out of the 41. Okay. So then we observe by the experience that out of those lines, how many lines are important, and then we set the relays. So this is regarding the setting of relays to provide the optimum protection. Now I have just compiled the data for 14 bus system regarding the experience, that what are the various problems in the protection in various subsystems. Now I summarize some of the points which may be of interest to you. That these are the computer-based approaches, and what are the problems with computer-based approaches. That too often engineering software asserts its degree of cleverness and projects itself so that only most dedicated specialist can master it. So this is a drawback. Further, degree to which these are interactive and user-friendly varies, and mostly full use of protection engineers' expertise and experience can be only partly utilized. So this is the problem with computer-based approaches. Now what computer-based software package should provide then? It should be made so that the direct benefit to experienced specialist user, that it directly benefits to experienced specialist user, but at the same time add some expert guidance to non-experienced users and less experienced staff also, so that they also might undertake tasks should it be required. And assistance to users as much as possible without need to remember cryptic code, bus number, etc. So balance between sophistication and expertness should be maintained. I have purposely tried to keep it simple without going into too much technical details. But my emphasis was to introduce the protection engineering subject, that how actually the protection is being given by the protective elements. Okay. Any query or any point which you would like to ask regarding this?